So we're going to continue on with number 12, and this will be video number part 2. So the number of electrons that can occupy an f orbital. An orbital is one of these m values. There are 7 f orbitals, but each one of these orbitals can only hold 2 electrons. So the answer I was looking for there is A. Then electrons that occupy the same orbital, they must have, remember over here, we had the positive spin and negative spin, so they must have opposite spins if they're in the same orbital. So 2 electrons in the same orbital would have opposite spins. Now, since opposite spins is not an answer, then you got to look for another answer that seems to be about right. So let's go back over here. You've got these electrons that are spinning clockwise and counterclockwise. And if they're in the same orbital, then they're in the same value, same value of m, is what I'm trying to say. So if you have 2 electrons in the m equals -1 and they're spinning in opposite directions, they're still in the same energy level, in the same sublevel, in the same orbital, so their energy is about the same. So that'd be your best answer, be almost the same energy. So that'd be B. Okay, the orbital notation for nitrogen contains how many unpaired electrons? Well, to do that, I'm just going to write it out here. So here's nitrogen's electrons organization. It's got a 1s, and it's got a 2s, and it's got a 2p. So you'd have that, you'd have that, you'd have this. So 1, 2, 3, 4, 5, 6, 7. The orbital notation would contain how many unpaired electrons? It'd be 3 of them. See them right here. 1, 2, 3 unpaired electrons. So the answer would be A. Which of the following is equal to the number of protons in a neutral atom? Well, if it's neutral, the positives and the negatives have to be the same. So what is the negative particle? The electrons. So the electrons and protons have to be the same in a neutral atom. Number 16, atoms of the same element that differ in the number of neutrons in their nucleus. Well, remember we had a couple different words. We had ions, we had isotopes. Ions are caused by loss or gain of electrons. So that's how you get charges or charged particles. And those numbers on your periodic table tell you what the charge would be if an atom lost or gained an electron. That's what the charge signs in the upper right-hand corner of your table represent. Isotopes are atoms of the same element. They have the same element, but they vary in the number of neutrons, which causes their mass to vary. So, for example, you might have carbon-12 or carbon-13 or carbon-14. They're all carbon, they all have 0 charge, but they have different weights because they have different numbers of neutrons. That brings us to 17. A certain atom consists of 16 protons, 16 neutrons, 16 electrons. What's its mass number? Well, mass number is protons plus neutrons. So P plus N equals mass. So 16 protons and 16 neutrons gives us 32. 32 is not a choice. Best answer was none of those. There. Same electron configuration. That would mean, there's another word for that, it's called iso, I have a hard time writing it, isoelectronic. I see down there, isoelectronic. So you'd look at the number of electrons and see if they're the same. If they're the same, they have the same configuration. So calcium has 20 electrons. Sulfur, -2, has 18 electrons. So 20 is not equal to 18. Chlorine has 17 electrons, but with a -1 charge, it has 18 electrons. Because a negative charge means you've gained an electron. Argon has 18 electrons all the time. So that's the same. Oh, there's your answer. So the answer is B, because they have the same electrons. All right, all the elements in group 14. So let's go grab a periodic table. We'll check out group 14. So it'll take me just a second to pull one up. maybe longer than a second. Maybe it'll take me a minute. All right, here we come with a periodic table. Okay, group 14 is this group right here. So all of them are in the P2 configuration. Remember, it goes 1s, 2s, 2p, 3s, 3p, and so on. But in the same column, they all have the same number in that particular sublevel. So this is all in the P sublevel block in the second column, so they all end in P2. Carbon ends in 2p2, so it's 1s2, 2s2, 2p2. Silicon ends in 3p2, 1s2, 2s2, 2p6, 3p2. Oh, I said that wrong. 1s2, 2s2, 2p6, 3s2, 3p2. Germanium ends in the same way, 4p2, and so on. So the answer to that one, number 19, is P2. Our irregularities occur in the D or F sublevel blocks. The D or the F sublevel blocks. So if you look at your periodic table, the D block starts here, goes to there. The D block starts here, goes there. So this whole area right here is the D block. The F block is down here. Over here is P's and S's. So irregularities will happen in this area or in this area. And specifically, it'll happen in the middle of this area, sort of in the middle area. If they're at the end, the very end, it's the last electron in, so they're filling up, and they're going to do what they're supposed to do. So, going back to the question, what were our choices? We had magnesium, zinc, chromium, and phosphorus. So we're looking for irregularities. Magnesium, not an answer. Chromium, good possibility that's going to be irregular. It's in D4 position. Zinc, it's in a D10 position. So it's going to do what it's supposed to do because it's the last one in the D sublevel block. It's going to fill in with 10 electrons. And then phosphorus was the other one, which is over here in the P block. So the answer's got to be chromium. That's the irregular one. It's one that's in the D block. So you expect those irregularities in the D and the F block. All right, so we'd look right here. We'd say chromium. Okay, how many paired electrons in the dot diagram of 10? Well, by now, you can probably realize that if you look over here, whoops. That you can determine the number of electrons in the outer shell by counting. So this is, that has a 1. This is 2. I can't write on this with my marker, but 1 in this column, 2 in this column. All these have 2 in their outer shell, then 3, 4, 5, 6, 7, 8. Except helium, which really should be over here. Okay, so we're looking for the number of dots, I think it was 10, wasn't it? How many paired electrons occur in the dot diagram of 10? So here's the dot diagram for 10. Notice that 10 is right here. It has 4 valence electrons. It's the second in the P sublevel, but before the 5P, there was a 5S. So you come back over here, I'll draw 10. S in, 4 valence electrons. The first 2 go into the S sublevel, and the next 2 go into the P sublevel. So that's the dot diagram. How many paired electrons are there? Well, I was looking for 2 electrons that are paired, because there they are, 1, 2 in the pair. I took either 1 or 2 because I didn't think the question was clear after I made it up. So this is the answer I was looking for, 2 paired electrons. But if you said 1 pair, I took that. 22, how many electrons are in the outer shell of manganese? Need the periodic table again for that. So I come back over here, the outer shell of manganese. So here's manganese, not magnesium, manganese. And that's 3D, but before the 3D, isn't there a 4S? So how many electrons are in the outer shell? It would be the 2 that are in the 4S, because 4 is higher than 3. So the answer for that was 2. In which do the D electrons never pair up? Now let's go back over to the periodic table again. So here's the periodic table, bring it back in. Okay, so if you're putting electrons in, get a little piece of paper to write on here. do it this way. So I'm going to make 5 orbitals. 1, 2, 3, 4, 5. So electrons are going to go in those one at a time. So that would be the electron over here in scandium. The next one would be, if I did titanium, it'd be right, oops, it'd be right there. Vanadium would add another electron, chromium another, and manganese another. So there's manganese. Okay, so after you get past manganese, you have to start pairing. Like that. So that would be iron. After iron, you'd have cobalt. Supposed to be an electron there. Then nickel, and so on. So you notice that these elements that I listed here, cobalt is in the D7 position, D7 position. I was right the first time. Nickel's in the D8 position. Copper's in the D9 position. Iron's in the D6 position. So all of them are more than 5, aren't they? The only one that's less than 5 is titanium. So that's your answer, because there's no pair of electrons in titanium. It's just a single done in the D sublevel. Which one has the same S and P configuration for n equals 3 that K does for n equals 4? Well, let's look over here. Here's K in the 4th series, right here. And Na is in the 3rd series. Wouldn't it have the same outer shell electron that K does in the 4th series? So I think the answer is Na. So answer would be A. Okay, the symbol of the elements that has the same electron dot notation as barium. So if you look at your periodic table, you'll find that calcium is in the same family that barium is in. So therefore, it's going to have the same dot notation. Barium's dot notation looks like this. Calcium dot notation looks like this. Kind of look the same, don't they? All right. Can I finish this page? I'll finish this page and we'll do the last page. All right, so 26. In the 4th series of elements, the first 2 elements have successive electrons in the 4s sublevel. After the 4s, what do they fill? What fills in? So, pull this aside. So here's the 4s. What follows the 4s? What's it say right there? 3d. So how many electrons go into the 3d? 10. So the next 10 elements fill in the 3d. Right. Now when we're doing dot notations, number 27, the only sublevels that can ever be in the outer shell are the S and the P, because the D sublevel is always preceded by a higher value of S. Let me show you that. So here's 3D. What's in front of it? 4S. Here's 4D. What's in front of that? 5S. And that holds true for Fs as well. See the F down here? But in front of that's a 6S. So the outer shell will either be S or S and P. So the answer I was looking for was E, but if you said S and P, I took C. I took that as well. Okay, the 5th energy of electrons in holmium. I think I mentioned to you in class that holmium is only popular in December. But if you look at holmium right here, it's right down here. So we're going to just go through the whole periodic table until we get to holmium. So we go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. There's part of our answer because it asks us for 5s electrons, or how many 5th energy level electrons. So let's just keep tab as we go. We got 2 there. All right, then as you move on, hello, there we go. So I was at 5s2, and then 4d10, and 5p6. Oh wait, there's more, 5p6, so we have 6 there. 6s2, 4f. Oh, and now we're going to run into holmium in 4f, which is going to be in the 4f, what, 14, 13, 12, 11, 4f11 situation, position. So holmium doesn't have any more 5th energy level electrons after 5p. So the answer would be 8. Okay, when an atom absorbs energy, what happens to its energy? Does it go up or go down? I just happen to have this little animation, so watch this electron. He absorbed energy. See, he moved from the, so I can't point on this animation, but watch the little blue dot in the center. It's going slow motion in the second energy level right now. Now he's on the first energy level, and light came off. You notice he doesn't always move up when something hits him. It has to be just the right amount of energy to make him go to a higher level. But there he went to a higher level. He's out on the 1, 2, 3, 4, 5, fifth level. Now fourth level. It's going to move again. And went down to the second level, and that blue light is going away. Kind of teal. And then down to the first level with ultraviolet light going away. Okay, so we'll get this out of the way. All right, so when an atom absorbs energy, its energy, of course, increases, and it increases by a definite quantity. Energy is quantized, and so it only absorbs certain amounts of energy. By the same token, the release of a quanta of energy, if it's releasing energy, it's going to decrease its energy, so the answer has to be C or B, but what is the formula for energy? It's h nu. And then 31, if I'm going to describe one single electron, I'm going to need how many quantum numbers? So I'll get this out of the way, go back to our little thing over here. So here's my quantum numbers. So I want to describe one electron. It's going to take an N quantum number, tell you what energy level. It's going to take an L quantum number to tell you what sublevel. It's going to take an M quantum number to tell you what orbital it's in. Then it's going to take a spin quantum number to tell you which way it's spinning. So how many quantum numbers was that? It was 4. And if they're in the same sublevel, how many quantum numbers do they have to have in common? Well, let's just pick this sublevel, for example, sublevel, this 3p. So if you have 2 electrons in the 3p, do they have to have 3 in common? Yes. Do they have to have p in common? Well, they're in the same sublevel, so they got to have that in common. Do the 2 electrons have to be in the same orbital if they're in the 3p? Or could they be in one of 3 different orbitals? So therefore, their orbital quantum number does not have to be in common if they're in the same sublevel. They have to have same N, same L, but M can be different. Do they have to be spinning the same way if they're in the same sublevel? Well, they have to be opposite ways, don't they? Or do they? They have to be the opposite ways in the same orbital, but they don't have to be opposite ways in the same sublevel. So 2 electrons in the same sublevel might be spinning the same way. For example, if I had 3 orbitals here, we'll say these are these 3p orbitals, -1, 0, 1. I have an electron here and an electron here. Do they have the same N value? Yes. Do they have the same L value? Yes. Are they spinning the same way? Yes. Are they in the same orbital? No. Or if I went on through the orbitals and went to a different element here still. Now, these 2 electrons in the same orbital, they have 3 quantum numbers in common. They have N, L, and M, but not S. Okay, so if 2 electrons are in the same sublevel, they've got to have 2 in common, and they might have 3, but they must have 2. And so the answer to that question is 2. They could have 3, and they can never have 4. In order to keep this from getting too long, I'm going to stop here. We'll pick up the next page later. I'll probably publish these 2 pages, and I may not get the next one done until tomorrow morning.